So to know the topic alkyl halides, we need to have some idea about nucleophilicity. So to understand nucleophilicity, we need to know what is nucleophile and what is a base. So first, nucleophiles. What are nucleophiles? We write it by the symbol Nu minus. So nucleophile is generally a negatively charged species or a species containing a lone pair which are on lookout of a positive center. Generally it will be a positive carbon center. For example, CH3 minus, because it has a negative charge, it wants to attack at any positive side. NH2 minus, OH minus can also be a nucleophile. The word nucleophile or nucleophilicity is a kinetic term, and nucleophilicity is inversely proportional to electronegativity of the central atom. If the electronegativity is high, it is not ready to give the electrons or attach at a positive site. If electronegativity is poor, it is readily available to attach at a positive site. That is why nucleophilicity is inversely proportional to electronegativity of the central atom. The next thing is about a base. Base is a species that abstracts a proton. Example is OH minus. So understand the term basicity is more related to thermodynamics. It's a thermodynamic term. We decide it by equilibrium constant. Nucleophilicity is decided by rate constant. Whether it's a good base or not is decided by the conjugate strength of that base. Conjugate base strength. That is conjugate acid base theory, which you have learnt in ionic equilibrium. So why we are speaking about these two terms? Because suppose if I speak about OH minus, it is a nucleophile, it is also a base. Why it's a nucleophile? It can attack at any positive center. Why it's a base? It can abstract a proton. Whether it functions as a base or whether it functions as a nucleophile is what we have to decide in that particular reaction. So for that we are learning some rules. Now suppose if I am speaking about different species which are present across a period, what is happening to nucleophilicity? To understand about nucleophilicity, we will understand through basicity. So if I am speaking about the elements, see, carbon, nitrogen, oxygen, fluorine are present. They are present across in the same period. So once they are present in the same period, what can I speak about them? Since they are present in the period left to right, what happens to electronegativity? Electronegativity is decreasing left to right. So most electronegativity is fluorine, least electronegative is carbon. So the nucleophilicity will be more for carbon, least for fluorine. That is why the nucleophilicity order is this. Also you can decide the same through basicity. What is basicity? Let us write the conjugate acid. The conjugate acid of F minus is HF. That is, if you add a proton, it will become the conjugate acid. So this is the acid. If you remove the proton, it becomes the conjugate base. The conjugate acid of OH minus is nothing but water. The conjugate base of this is nothing but ammonia. The conjugate base of this is nothing but methane. Out of all of this, HF is most acidic. This is most acidic. This is an acid. So that means F minus, the conjugate base, is very weak base. The acid and its conjugate base are opposites in strength. You have learned this in ionic equilibrium, you have to keep in mind. So this is strong acid, this is weak base. If you take methane, it is not even an acid. So I can call it relatively weak acid. That means the conjugate base is strong base. So if it is strong base and nucleophilicity is same as basicity across a period, so this will be the strongest nucleophile. That is how we are deciding nucleophilicity across a period. So either decide by electronegativity of the atom or by the acid base strength, that is by basicity. So if for people who don't know what is conjugate acid base strength, if HA is the acid, after giving a proton it becomes H plus and A minus is the base. So this is the acid and this is the conjugate base. This is the conjugate base. If you say the acid is strong, if this is strong acid, automatically that means dissociation is occurring more. So that means the base is weak. It can't accept the proton and go back in the reverse direction. If you are saying it's a weak acid, that means dissociation is occurring less, or A minus is attaching to the proton back and forming the acid back. That means association is occurring more. So if the acid is weak, the base is strong. If the acid is strong, the base is weak. That is conjugate acid-base theory. Next, what happens to nucleophilicity down the group? Down the group, again nucleophilicity is inversely proportional to basicity. It is different. So what is nucleophilicity down the group? I am saying nucleophilicity increases down the group. That means if you take fluorine, chlorine, bromine, iodine, iodine has the highest nucleophilicity, whereas fluorine has the least nucleophilicity. What is the basicity order? Basicity order, F minus is the strongest base. F minus is strongest base. How do you decide about them? So you have to write from their conjugate acids. If you look at HF and HI, HI is strong acid. Why? It can dissociate more easily to H plus and I minus. Why? I minus is big in size, so charge density is less, so it will not take up the H plus easily. Whereas if you compare F minus is small in size, so negative charge is present in a very small area, so it will abstract the H plus back. That means it will form HF back, which indirectly means HF is not dissociating, which means it is a weak acid. So HF is weak acid, HI is strong acid. If HI is strong acid, I minus, which is the conjugate base, is the weak base. HF, if it is weak acid, F minus, which is the conjugate base, is the strong base. So if it is strong base, its nucleophilicity is least, because nucleophilicity is inversely proportional to basicity down the group. That is how, with the help of basicity, we are deciding nucleophilicity. Now we have a special case where the donating atom is same. Here donating atom or the central atom is oxygen, which is holding the negative charge, oxygen. In such a case, how to decide the nucleophilicity? Because we can't speak in terms of period and group. In such a case, again decide by the conjugate base strength. This is carboxylate ion from carboxylic acid. This is phenoxide ion from phenol. This is alkoxide ion from alcohol. Among all of them, carboxylic acid is an acid. Relatively it is stronger, whereas alcohol is not even an acid. So call it as a weak acid. Phenol lies in between. So if it is strong acid, the conjugate base will be weak. If it is weak acid, the conjugate base will be strong. So if it is strong conjugate base, then it will be a better nucleophile. If it is weak conjugate base, it will be a poor nucleophile. So the nucleophilicity order is this. RO minus or alkoxides are better nucleophiles. This is how you decide nucleophilicity. Why we are speaking about nucleophilicity? If you know whether it's a good nucleophile, then you can say that substitution, nucleophilic substitution reaction can occur. If you say it's a good base but not a good nucleophile, then you have to say base will undergo elimination reaction. I have to discuss one more special case. The case is, so this is like an exception you may think. The case is when I have a tertiary alkoxide, whereas with a just ethoxide. So here nucleophilicity again is decided by the amount of charge present. All these three carbon atoms are plus I groups. They increase the negative charge density. This is tertiary butoxide. This is just ethoxide. So among all of them, now nucleophilicity, if the atom is same, nucleophilicity should parallel basicity. Now this is a strong base. Because of plus I effect, negative charge is increasing, so it can abstract proton back. There are only two carbon atoms, so this is a primary carbon atom, you can say. So because of this, relatively this is a weak base. But since this is bulky and nucleophilicity is a kinetic term, this nucleophile has to go and attack at some positive carbon center. When this is trying to attack at a positive carbon center, there will be steric repulsions between these groups and the remaining groups of that carbon. So because of steric factor, that is because it is bulky, though it is a strong base, it behaves as a poor nucleophile. That is the exception. So bulky base, even though it is a strong base, or you can say it should be a strong nucleophile, it is behaving like a poor nucleophile because of the steric factor. That is the exception you have to keep in mind.